Okay, we're trying to find limits of piecewise functions. And looking at our equations, most of your equations of your piecewise functions are going to be continuous, all real, always limit having functions. Except at, well, probably, maybe, if it's going to be at that place. Okay, so this is the interesting part. These are the restrictions on your graphs, right? The ones that divide it into the different pieces of your graph. So we're going to really be seeing what is going on at that point. Really that point only. So the majority of this is just to have practice with graphing. So we have to the left of 0 the graph of 2x plus 3. So the graph of 2x plus 3 has a y-intercept of positive 3. Oh, that's not a closed circle. That's an open circle because it says less than 0. So at 0, the 2x plus 3 is going to have an open circle. And then it has a slope of positive 2. So what would normally be up 2 and right 1, right, that's a positive 2 slope. Since we can't graph it to the right side of 0, we're going to instead get all of our points by going down 2 and left 1. So we're going to get all of these extra points from 2x plus 3 by using our slope. Down 2, left 1, down 2, left 1, down 2, left 1. So here's the graph of 2x plus 3. Right? It's a linear graph. The limit exists everywhere on this linear graph. Okay, the different y values. Just pick any x and you'll figure out what the limit is going to that y value. Okay, so now we're looking at our other graph of x squared minus 4. So x squared minus 4 is a parabola that's been moved down 4 units on your y-axis. So from our origin, we go down 4 units. So we have a vertex at 0, negative 4. And then we're going to use our standard parabola pattern. So if you go 1 unit to the right, your point is 1 unit up, because 1 squared is 1. Okay, and then if you go back to your vertex and we go over 2 units, 2 squared is 4, so we go up 4 units to get our next point. And if we were so inclined, we could go back to your vertex and go over 3 units. 3 squared is 9, so we would go up to here, and we would make our graph of x squared minus 4 by connecting these interesting points. Okay? So formally, we're going to look at the limit from the left and the limit from the right. So we're going to evaluate what is the limit as x approaches 0 from the left. So this little minus that you put up above your number. Okay, and it always goes in the upper right, sort of like where you would put an exponent. But these are not exponents. This means from the left side of 0. Okay, that's what that little minus means. Okay, so we're coming from the left side, so let's make a little graph of that. So we're going to come from the left side, and our y value approaches what from the left side? The y value approaches 3. Okay, so the left-hand limit of our function as x approaches 0 is positive 3. Okay, now we're going to compare that to the limit from the right. So we write limit as x approaches 0, and we put a little plus up there in the quote-unquote exponent spot. Plus means we're going towards 0 from the right side. So 3, 2, 1, 1/2, right? We're getting closer and closer to 0 from the right side. Okay, and what y value does that approach if we're going from the right? Negative 4. Okay, so formally we would say, right after we showed this work on our paper, which we did a great job of, we would say that the limits as x approaches 0 from the left of our function does not equal the limit as x approaches 0 from the right of our function. Okay, the limit from the left does not equal the limit from the right. Okay, so we showed our work, right? This is our work. We show that this is positive 3 from the left and negative 4 from the right. So clearly those things are not equal. Okay, so that is our analysis. Now we make our conclusion. Therefore, so we're going to use these 3 little dots in a triangular pattern. This is the symbolic representation for the word therefore. If you want to be wonderfully English language arts and write out therefore every time, go ahead. If you want to be mathematically symbolic and look impressive, then use the 3 dots. Therefore, what can we say about the limit as x approaches 0 if the left and the right don't match up? Does not exist. Okay, so 0 would be the c value for which the limit does not exist, right? And it's the only interesting one up there. Those are the restrictions on your piecewise function to begin with. Okay, so this is very formal, right? This is a very formal justification of the reason why the limit does not exist. You look at the left-hand limit and you compute the right-hand limit. You analyze them, right? You say that they are not the same. Therefore, the limit at 0, right? This is the one we're looking at 0 of our function does not exist. Okay, that's very AP of you. All right, number 2. Now we have 3 graphs and 2 places to look at. So negative 3, right, is going to be one of our restrictions, and positive 2 is going to be the other restriction. So we have an absolute value graph. When was the last time you did an absolute value graph? Right, never. So we're going to look at a V, absolute values graph to V's. But since it has a negative in front, our V is going to be going down. We're going to have a downward facing V. That is 5 units to the left of the origin and 3 units up. Okay, so we're going to go 5 units to the left and 3 units up, and that's where we're going to put our quote-unquote vertex, and then we're going to make our parabola open down. So there we have our absolute value graph. Okay, between negative 3 and positive 2, we're going to graph x plus 1, that linear function. Okay, so this linear function has a y-intercept of positive 1, and it has a positive 1 slope. So up 1 over 1 is how we get our points. And at positive 2, you're going to have an open circle because it's less than positive 2. Okay, and also we'll continue on to the left until we get to negative 3, where we also have another open circle. So this is our graph of x plus 1. Okay, and our last one, this one is an absolute, no, this one is a square root function. A square root function that has been moved 2 units to the right, 3 units up, and then opens down. Okay, usually our square root function would grow like this, but since it's a negative one, it's going to open up underneath. So it's going to be a downward growing absolute or square root function. Okay, so we have 2 units right and 3 units up. That puts us right here at the end of your middle graph. So if we go 1 in the right, what's the square root of 1? 1. So 1, 1 is another point, but it's 1 down because it's negative. If we go 4 units to the right, what's the square root of 4? 2, and it's 2 down because it's negative. So our square root graph would look like this. There we go. That has an open hole. So looking at our graph, we can tell that as x approaches, let's see, the limit as x approaches negative 3 of our function does not exist. Okay, the limit from the left goes to positive 1. The limit from the right goes to negative 2. So the left limit does not equal the right limit, therefore the limit does not exist. But at positive 2, the left limit goes to positive 3. And the right limit also goes to positive 3. So we can say that the limit as x approaches 2 of our function is in fact positive 3, because the left and the right do go to the same place. Okay, so the limit does not exist as x approaches negative 3, because the left and the right don't match up. Okay, but say we weren't given a grid, or you don't know what the graph looks like. It could be something crazy. How would we deal with that? Well, we deal with that by looking at your restrictions, right? This is the only place that we're really concerned about. For a square root function, right, that is a continuous function on its domain. So anytime we have a continuous function, there are always limits are existing. And we have a quadratic, which is also a continuous function, so the limit exists everywhere there. So we're only really concerned about negative 2. So how we do is plug negative 2 into the top equation and plug negative 2 into the bottom equation. And look at their y values. If their y values are the same thing, then your graph limit goes to that value. Okay, so let's check it out. So let's see, g of x. So let's plug negative 2 into our top function, the square root. So negative 2 plus 6 minus 2. Okay, so g of negative 2. We plug negative 2 in. This gives us the square root of 4. The square root of 4 is positive 2. 2 minus 2 is 0. Okay, so we can say that the limit as x approaches negative 2 from the left, right? So less than things are on the left side. So as x approaches negative 2 from the left of our function g of x is 0. Okay, because that's the y value of our graph at negative 2 from your square root portion. So now let's plug it into the quadratic portion. Negative 2 plus 1 squared minus 1. Okay, so that's negative 1 squared minus 1. Negative 1 squared is positive 1. 1 minus 1 is 0. So the limit as x approaches negative 2 from the right of your function is 0. Okay, so without a graph, you can still figure out what the y values are. And as long as the y value from the left matches up with the y value from the right, we can conclude that the limits at that point, so exactly at negative 2, of our function g equals 0. Okay, so we don't have to make a graph. I mean, if you love doing graphs, by all means, make a graph. But on the AP test, you're limited by time. You only have 15 minutes or so per multiple choice or per FRQ. So we don't want to waste time doing things that don't help us come to our conclusion. Okay, so one last one here. If any values exist, what are they for your p function? Okay, so we're going to do, once again, the thing is to plug negative 1 into both of your equations and see what their y value is. So we have 0 from our top function, or from the left, right? Less than means from the left. So the limits as x approaches negative 1 from the left of our p function does not equal the limit as x approaches negative 1 from the right of our p function. We have to talk about what function are we talking about. Okay, what function? So we have our p versus our g versus your f, and where are we talking about it specifically? Right, so at negative 1 from the left of our function does not equal negative 1 from the right of our function. Therefore, the limit as x approaches negative 1 of our function does not exist.